Everything you can see, touch, or measure, every star, every planet, every atom, came from somewhere. And that somewhere is a moment we call the Big Bang. But here is the interesting part. The Big Bang was not an explosion in space. It was the moment space itself began, and then, almost instantly, it grew at a speed that makes your head spin. That moment of incredibly fast growth has a name: cosmic inflation. And understanding it changes how we think about everything, where we came from, and what the universe looks like beyond what we can see. So let us start from the very beginning. And I mean the very, very beginning. When scientists say, before the Big Bang, they hit a wall. Our physics simply stops working. So instead, let us ask a better question. What was the universe like in its very first moments? It was unimaginably hot. Every particle that will ever exist was crammed into an incredibly tiny point. We are not talking about the size of a city, or a marble. We are talking about something far smaller than a single atom. Now here is where it gets fascinating. At that scale, the rules of physics are different. Quantum effects take over. And one of those quantum rules says that even empty space is not really empty. It bubbles with tiny fluctuations. These tiny fluctuations matter enormously. We will come back to them, because they seed everything we see in the universe today. But first, we need to understand what inflation actually is. And to do that, we need one key idea: energy in empty space. This might sound strange, but space itself can carry energy. Not particles, not light, just space. Physicists call this vacuum energy. And when the universe was brand new, the vacuum had an enormous amount of it. Think of it like a ball sitting at the top of a hill. It has stored energy, potential energy, just waiting to be released. In the early universe, space was like that ball, sitting at the top of the hill, full of energy, but not yet released. And here is the key: this stored energy in space acts like the opposite of gravity. Instead of pulling things together, it pushes space apart. Scientists call this a scalar field, a kind of energy field spread across all of space. During inflation, it goes by a specific name: the inflaton field. That is the field responsible for inflation. Think of it as the engine that drove the universe's incredible growth. While this field was active, it pushed space outward, faster and faster, with no friction, no slowdown, nothing stopping it. Now let us talk about speed. Because inflation was not just fast, it was so fast, the word fast almost doesn't apply. In about 1/1,000,000th of a billionth of a billionth of a billionth of a second, the universe grew by an unimaginable factor. To give you a comparison, imagine something the size of an atom growing to become larger than the observable universe. Not just a bit larger, many, many, many times larger. That is the scale of inflation. And here is the part that makes this interesting: nothing moved faster than light. Space itself expanded. This is a crucial difference. Einstein said nothing can travel through space faster than light. But space itself has no speed limit. So during inflation, 2 points in the universe could be separated faster than light could ever connect them. And that fact has huge consequences. We will explore those consequences in detail, but first, let us ask, why did inflation stop? Inflation could not last forever. The inflaton field eventually lost its energy, like a ball finally rolling down the hill. When the ball reaches the bottom, when the inflaton field settles, all that stored energy has to go somewhere. That energy converted into an enormous burst of particles and heat. This is the moment scientists call reheating. Reheating flooded the universe with the building blocks of matter, quarks, electrons, photons, everything that will eventually become you. And this is where the Big Bang picks up. What we usually call the Big Bang happens right after inflation ends. So inflation is not the Big Bang. It is what happened just before, and it set the stage for everything that followed. Now here is the big question. Do we actually have evidence for this? How do we know inflation happened? The best evidence for inflation is indirect. It solves problems that nothing else can explain. Let us look at those problems one by one. Problem 1. The universe looks the same in every direction we look. Same temperature, same density, almost perfectly uniform. But here is why that is strange. The light coming from opposite sides of the sky has never had time to interact. They should not know what temperature to be. Imagine two people on opposite ends of Earth who have never spoken, somehow wearing exactly the same outfit. How? This is called the horizon problem. And inflation solves it elegantly. Before inflation, those regions were incredibly close together. They had time to reach the same temperature before inflation ripped him apart. The uniform universe makes perfect sense. Problem 2. The universe is geometrically flat. If you draw a triangle across 1 billion light years, its angles add up to exactly 180 degrees. But why flat? The universe could have been curved like a ball, or curved like a saddle. Flat is a very special case. Let us spend a moment on the flatness problem because it is more remarkable than it sounds. For the universe to be flat today, the density of matter and energy in the early universe had to be tuned to incredible precision. Scientists calculated that the density had to match the critical value to within 1 part in 10 to the power of 60. That kind of precision, without some mechanism to explain it, looks like an extraordinary coincidence. Inflation removes the coincidence. If the universe started as anything even close to flat, inflation would stretch it into near-perfect flatness automatically. Now we get to one of the most extraordinary ideas in all of science. The galaxies you see in the night sky began as quantum fluctuations. Remember, empty space at the quantum scale is not truly empty. It has random, tiny ripples of energy. Normally, these ripples are unimaginably small. They exist for a fraction of a second and then cancel out. But during inflation, space was expanding so fast that these pairs were ripped apart before they could cancel. When that happens, those fluctuations become real, permanent variations in the density of space. Some regions are slightly denser. Some are slightly emptier. The differences are tiny, but they are enough. Because gravity works on those density differences over billions of years. Denser regions pull in more matter. The slightly denser spots become galaxies. The slightly emptier spots become cosmic voids, vast empty stretches of space. So the large-scale structure of the entire universe, the web of galaxies we observe, is a direct imprint of quantum randomness, blown up by inflation. This prediction can be tested. And when we look at the sky, we find exactly the pattern that inflation predicts. Our best window into inflation comes from a faint glow that fills the entire sky. It is called the cosmic microwave background, or CMB. The CMB is light from 380,000 years after the Big Bang, the first moment the universe became transparent enough for light to travel freely. Before that, the universe was a hot dense fog. Photons couldn't travel anywhere, they kept bumping into particles. Then the universe cooled enough for electrons and protons to combine into atoms. Suddenly the fog cleared. The light released at that moment has been traveling ever since, stretched and cooled by the expansion of space into microwave radiation. When we map the CMB across the whole sky, we see a nearly uniform temperature, but with tiny variations. Hotter and cooler patches. Those tiny temperature differences are the density variations from inflation, imprinted on the sky. Inflation predicts a very specific pattern to these fluctuations. The variations should be nearly the same at all scales, called scale invariance. And when satellites like WMAP and Planck measured the CMB in exquisite detail, they found exactly that pattern. This is not just a coincidence, it is a precise quantitative match between theory and observation. A major reason physicists take inflation seriously. Cosmic inflation was first proposed in 1980 by a physicist named Alan Guth. He was trying to solve exactly the problems we just described. Guth realized that a brief period of exponential expansion in the early universe would solve all three problems simultaneously. He called his original idea, old inflation. It had a flaw: the end of inflation was too abrupt and created a non-uniform universe. Physicists André Linde, and independently Paul Steinhardt and Andreas Albrecht, fixed this with a smoother version called new inflation. And Linde later developed chaotic inflation, the idea that inflation could start from almost any initial condition, making it even more robust. Here is where things get philosophically interesting. Inflation may not have ended everywhere at the same time. Because the inflaton field has quantum fluctuations, in some regions it ends, and in other regions it keeps going. In the regions where it ends, a universe like ours forms. In the regions where it keeps going, space keeps expanding. This creates a situation called eternal inflation, where inflation never truly stops everywhere. It keeps spawning new regions. Each of these regions that stops inflating could form a universe with potentially different physical properties. This collection of bubble universes is what people call the multiverse. It is a mathematical consequence of eternal inflation. Now, here is something important. The multiverse is a prediction, but not yet a testable one. We cannot observe other universes directly. Some physicists find it compelling, a natural result of a valid theory. Others are cautious because unfalsifiable ideas are not strictly science. Either way, understanding eternal inflation shows us just how large the consequences of those first moments truly are. Scientists are searching for a direct smoking gun signal of inflation. And they think they know what to look for: gravitational waves. When space inflated, the quantum fluctuations that created density variations also created ripples in spacetime itself. These are called primordial gravitational waves. They should be imprinted on the CMB in a very specific way, as a pattern called B-mode polarization. B-modes look like curls. Other processes create straight patterns called E-modes. Only inflation produces the curl pattern. In 2014, an experiment called BICEP2 announced they had found B-modes. Scientists were excited. Had they found proof of inflation? Unfortunately, after a careful comparison with Planck satellite data, the signal turned out to be dust within our own galaxy, not a primordial signal. But the search continues. New experiments, BICEP array, Lightbird, CMBS4, are specifically designed to detect primordial B-modes. Detecting primordial B-modes would be one of the greatest scientific discoveries in history. It would be direct evidence that inflation happened. Let us take a step back and think about what inflation means for the size of the universe. We can only see a finite part of the universe, the observable universe, because light has only had 13.8 billion years to reach us. Beyond that, we cannot see, not because there is nothing there, but because light hasn't had time to arrive. But inflation tells us the full universe is vastly larger than what we can see. How much larger? Almost certainly enormous. Remember, inflation stretched the universe by an enormous factor. Our observable region is just one small patch of the whole. This also means the regions just beyond what we can see should look very similar to ours, because they inflated from the same original patch. Only on much larger scales, far beyond our horizon, might you start to find regions with genuinely different properties. Here is a question that might seem unrelated. Why does time only move forward? Why can't we remember the future? Physics equations mostly work in both time directions. Falling forward looks like falling backward in reverse, mathematically identical. What breaks the symmetry is something called entropy, the tendency of systems to move from order to disorder. For entropy to increase, the universe must have started in a very low entropy, very ordered state. Inflation provides a natural explanation for this. The inflaton field is a very special, highly ordered state of the universe. When it rolls down and releases energy, it produces a hot, dense universe that is still highly ordered compared to what comes later. So inflation may be responsible not just for the structure of the universe, but for why time has a direction at all. Now, inflation is not one specific theory, it is a framework. Many different models try to explain the details. All models agree on the basic idea: exponential expansion driven by a scalar field. But they disagree on the shape of the energy hill. The shape of that hill determines how inflation ends, how long it lasts, and what imprint it leaves on the CMB. One popular class is called slow roll inflation. Here the energy hill is very flat. The ball rolls down slowly and gradually. Slow roll models are popular because they naturally produce the scale invariant spectrum we actually see in CMB data. Another class is Starobinsky inflation, proposed by Alexei Starobinsky in 1980, independently of Guth. This is currently one of the best fitting models to data. Upcoming CMB experiments will measure the CMB spectrum with enough precision to rule out most models. They will zero in on the correct one. Inflation solves a lot of problems. But it also comes with open questions, and being honest about those is important. First open question: what exactly is the inflaton field? We have never detected it directly. We don't know what it is made of. Second, what started inflation? What set the ball at the top of the hill in the first place? Third, how do we test the multiverse? If inflation is eternal, most of its predictions live in regions we can never observe. Fourth, some physicists argue inflation is too flexible. With enough models, it can predict almost any result, which makes it hard to falsify. These are serious debates happening right now in physics. Scientists like Roger Penrose and Paul Steinhardt have proposed alternatives to inflation. The honest answer is, inflation is the best framework we have. But the work of confirming it, or replacing it, is still ongoing. Let us connect everything we have learned into one complete picture. Step 1. The universe begins in an unimaginably small, hot, quantum state. Step 2. The inflaton field dominates. Space undergoes exponential expansion, inflation. During inflation, quantum fluctuations are stretched into real density variations across the universe. Step 3. Inflation ends. Reheating fills the universe with particles and energy. The Big Bang era begins. Step 4. Over the next 380,000 years the universe cools. Light is released. The CMB forms. Step 5. Over hundreds of millions of years, gravity amplifies the density variations from inflation into galaxies and large-scale structure. And today, 13.8 billion years later, we sit inside one of those galaxies. We can look back at the CMB to see the very imprint of inflation. You might be wondering, why should any of this matter to me? Inflation happened 13.8 billion years ago in a fraction of a second. Here is why it matters. Every pattern we see in the universe today, every galaxy, every cluster, every void, was set up by inflation. The atoms in your body were forged in stars that formed in galaxies that formed from density variations that inflation created. Inflation also humbles us. If eternal inflation is correct, our entire universe, with its 100 billion galaxies, might be one tiny bubble in something far larger. And every measurement we make of the CMB, every gravitational wave experiment, every telescope pointed at the sky, is a vote in this big question. Science does not demand certainty. It demands evidence. And with every observation, we understand the first moments of the universe a little more. Cosmic inflation tells us that the universe we see, in all its staggering size and complexity, may be the echo of a tiny quantum ripple in the first trillionth of a second. And that, to me, is one of the most remarkable things we have ever figured out. Keep asking why. Keep looking at the sky. The universe started talking to us 13.8 billion years ago, and we are only just learning to listen.